I think, first of all, when we talk about classical mechanics, we're talking about F equals ma. At
That's
the
as much classical as you can get.
right, like
Yeah.
that's where it pretty much started, saying that the sum of forces on an object is just a mass times the acceleration. And yeah, it's a pretty simple statement. You learn that in high school. They give you a situation where, you have a block, someone's pushing on it, and then it's also falling due to gravity, and then you got to calculate like its trajectory or something. I guess that would be a little bit more complicated.
Yeah, no, the
Now
falling
that-
block would be a little more complicated. I think the simple example is, well, just take any cart, like a frictionless cart, and you put it with like 5 newtons. What's the
Okay,
initial
yeah,
acceleration,
sure.
for example, is a much
Sure.
easier
Sure.
idea. And I think also what that also it also states that the sum of all external forces is equal to ma, because that's also important, because
Yeah.
a little bit later on you also come to internal forces in a system, and you come to the astonishing result that internal forces don't actually matter at all.
Yeah, but this is the reason why you can't jump and like push yourself and then like go in a direction.
Exactly.
Or if you're in an elevator, you can't. We've had this conversation.
We've had this very
before.
same conversation.
But anything that happens, you see those like stupid posts on Facebook where it's like, oh, like just stand in a bucket and then pull the sides up so you'll float. It's like, no.
Wait, stand. I've never seen it. Stand in a bucket
It's like
and
you
pull the
stand in a
sides up.
bucket and like you hold the lever and then
Okay.
you pull on it and then you'll move up. It makes no sense.
What?
It's
That's
no,
just not
because
how
the-
physics works.
The forces are all in the system, and
Yeah.
so it's all internal, so it doesn't matter. And this is actually true in general. Like, if you consider the entire universe as a system, then like nothing interesting really happens because everything just cancels out. Under the assumptions of classical mechanics and not an accelerating.
There are a lot of
universe.
exactly.
What would that mean? What would that if the universe accelerates? Like, what would that mean?
Well, I mean, it is accelerating in our
No, I know,
latest
but
theories.
but like, is there a force, an internal force that
dark
is
energy.
causing it to accelerate? So I guess F equals ma doesn't count in that case because the internal force is making something accelerate.
No,
but I
but
guess
I
there's
don't
a
think
whole-
I don't think dark energy is okay. Yeah, I don't really
No,
know.
but
how
there's a
that's-
whole bunch of like other things that don't really make sense because in this case, we're not talking about an object accelerating. We're talking about the boundary of existence accelerating. So like, is that even an
Yeah.
object?
It's not.
that
Yeah, because,
has
because
mass.
there was the whole thing about like information traveling faster than the speed of light, but
Yeah.
then that's not really information. Like the
Yeah.
whole quantum
Yeah.
entanglement. So like I think that kind of might be in the same line as this,
Mm-hmm.
that it's just the boundary. So it's not like a physical object that's accelerating. So that's why technically the boundary is, I think, like relative observers is like accelerating faster than the speed of light, right? So I'm pretty sure at some point there's literally going to be the boundary to someone accelerating faster than light, which makes no sense, which is why it doesn't exactly get covered under the information. So it can do whatever it wants. It's kind of like
guess.
outside the bounds of what we say are objects.
But yeah, I guess coming back to classical mechanics, you learn in high school about forces, friction, and energy. Energy is actually really interesting, and actually, I don't know if we're going to get to this today, but we're definitely going to make another episode about Lagrangian mechanics and also Hamiltonian mechanics, because those are so beautiful. And the analogy in like from electrodynamics is so awesome. How in electrodynamics or just electrostatics, you have the electric potential, which is just a scalar potential. It's just one value. It just has a scalar value at every point in space. And then when you get to magnetostatics, you have a vector potential where the potential is described by a vector at every point in space, which is harder to calculate just because it's a vector. And also, it's just like weirder in general. But now, same thing with, well, the point of saying that is that it's much easier to deal with scalars than vectors. And in the case of Newtonian mechanics, F equals ma, you're figuring out, like in solving a problem, you're figuring out the forces, which usually are three-dimensional vectors acting on an object. And so you're gathering up all these three-dimensional vectors and then solving for the motion of your object. But you know what's easier than vectors is scalars. And you know what's a scalar? Energy is a scalar. And so when we do end up talking about Lagrangian mechanics later on, we're going to see how instead of gathering up all these three-dimensional vectors, you can gather up instead properties of the system that are one-dimensional, just scalar values, like the kinetic energy and the potential energy. And then from there, I'm not going to get into all the details of it, but you can get the exact same equations from F equals ma, but through energy.
So I mean, I think we could like dabble on into it a little bit later on this episode, because I mean, Lagrangian mechanics is classical mechanics.
No, it is, yeah. It's just a different way to do it, right?
Yeah. So okay,
because it's equivalent.
So one way, okay, if there's anything to be known about classical mechanics for, let's say, people that are listening that are like, what really is classical mechanics? It's really a culmination of multiple different techniques. The very first one, the Newtonian mechanics, is kind of like the forefront of classical mechanics.
Yeah.
I believe there probably was multiple scientists before that started it, but
nowadays though, Newtonian mechanics is pretty synonymous with classical mechanics, because you don't touch Lagrangian or Hamiltonian until you get to third year.
No, but remember, Lagrangian is very basic classical mechanics.
No,
too.
I know, but there's no way anyone's going to know about that before they get into...
Oh, yes, for sure. Before they get into any higher academic, for sure. But yeah, so Newtonian is what like everybody knows, everybody's familiar with, because it's also like the easiest, also because it comes from just the first three principles, which make a lot of sense. Like the very first law, like that's basically like, if you think about it, like the first principles of classical mechanics, like Newton's first three laws. And they kind of describe a lot about how the universe should work.
And you know what's funny is that if you were to plot the difficulty of problems that you can solve versus difficulty of the method versus difficulty of the problems that you can solve, the Newtonian method has a very high gradient. But it intercepts zero.
Of course.
It intercepts zero, meaning beginners can start. But
I understand
the gradient is very high, meaning as soon as you start to get a little bit complicated, like it becomes so difficult.
Because the moment your system gets complicated, as you just said, you have to take into consideration all these three-dimensional forces.
Exactly. But at some point, it makes more sense to switch to Lagrangian mechanics, because the intercept is actually not zero. It's very high, which means like beginners can't start there, but the gradient is much lower, which means that when Newtonian mechanics, that line intercepts the one for Lagrangian mechanics, it makes so much more sense to just hop onto the other one, because now you can start solving much more complicated problems without putting in that much more effort, because you understand how it works. Now it's just applying your problem. Like you have a question where it's like a rope around a pulley doing a dance, and you just apply all the things, all the kinetic, the potential, and then you just plug it into the thing, and you're done.